Okay, so I believe that you all have watched the video, pre-recorded videos regarding these chapters on um, the risk assessments or the calculations of all the probabilities and also inventory fault tree. Okay, do note that inventory and fault trees are very useful tools in the real industrial environment. So first we will just look at these two questions because I think there's only two questions today. Yeah, part one and part two questions. Yep. So what we will focus on is the calculations on the first questions to study what is the mean time between failure of this whole system. This is especially useful for those who are going to work as the maintenance or what we call equipment engineer, because you need to know like your system, how frequent that it might break down. And therefore, you can then plan for your preventive maintenance, because we don't just throw out preventive maintenance and say, oh, I'm going to do PM every 3 months or every 6 months or every 1 year, because with data support, okay, someone asked me will I start recording. Okay, yes. So with the data to support us, only then we will be able to know, okay, is 3 months sufficient? Like if let's say the mean time between failure is every 6 months, then perhaps a maintenance of every 5 months will be sufficient. You don't have to do it every 3 months, you know. And if let's say the whole system is so stable, it will only break down once every 2 years. So perhaps a yearly or 18 months maintenance is required. That is how the calculations, or that's how the management or the maintenance team decide how often is required for their system to run the PM, to down the system, to change the parts, or to even service it. Okay, that is why we study this chapter to study what is the fault or the failure per year, per equipment or per instruments. And then we calculate for the entire process. Yeah. Okay, so the water flow to a chemical reactor cooling coil is controlled by the system shown in this figure, and the flow is measured by a flow transmitter, and the controller and the control valve manipulate the flow of the liquid. Calculates the overall failure rate, the unreliability, the reliability, and the mean time between failure for the system. Okay, so what I did is that I have copied the table for you to see over here. Let me enlarge it a little bit so you can see. So these are the general, or I would say the average of instruments that the breakdowns per year. So they call it faults per year. Like for example, controller is 0.29 per year, meaning if let's say we calculate 1 divided by 0.29 is like it basically break down every 3.5 months in general. Okay, control valve 1 over 0.6 will be every 1 year, every 1.6 years. Okay, or 1.6 months it break down. Sorry, I don't think that's the data. Fault per year, so 0.29 divided. Yeah. So every year it will have 3.5 faults around there. Okay. And 0.6 times 12. So every 7.2 months, sorry, for control valve, it will be 7.2 months average, it will break down and so on. So this is how we calculate this system. Okay, so in that case, we will start with the reliability of each system. Okay, each data here. So reliability is given by the formula mu over t, mu times t, where mu is the fault per year, okay, which is this data. So this is mu, okay, and the time is 1 year, okay. So in that case, you can straight away use, let me just open up my calculator. So in that case, your RT for what we have here, we have this one. So we have a control transmitter, okay, and a controller, and also a measurement. Okay, so basically we have these three: controller, control valves, which is this one, and also our flow measurements, which is your flow transmitter. Okay, so E minus 0.29 T. So what do we have? We have 0.748. Okay, where T is 1, because we're talking about yearly basis. Okay, so then same thing, if let's say this is, the first one is the controller. So the next one we have the transmitter, the FT. So E minus flow measurements 1.14. Okay, we get something like 0.3198. And also we have our R WAF. .60. So you get 0.5488. Okay, so now we want to know what is our overall reliability. Okay, hold on. Let me just make this small because we no longer need this one, so that I have more space to write. In that case, the overall, R overall, okay, is given by the formulas. This one, big phi n I equals 1 R I. Okay, so what does this symbols mean? This is, if let's say we have summations, means we add everything. And when we have this phi, means we times everything up. Okay, in that case, it will be 0.7483 times 0.3198 times 0.5488. Okay, and we get 0.1313. Again, so this one is just the R reliability value. So we want to know the overall failure rate per year, okay, which is our mu T. So just now we use individual T to calculate, okay, the overall here. So now again, we use back the same formula, R equals to E minus mu T, okay. In this case, it will get minus mu 1 year equals to ln 0.1313. Okay, so we should get negative 2.03, and so your total per year is 2.03 failure per year. Okay, so this is how we calculate the overall failure rate. Okay, so now we want to calculate what is the process unreliability of the year. Okay, so process unreliability is given as P total equals to 1 point minus RT, because unreliability plus reliability is 100%. Yeah, so it's like how reliable is the system and how unreliable is the system. So unreliability is just 1 minus this value, 0.1313. You get 0.8687. Okay, so that's the overall process unreliability. And now if we are to calculate what is the mean time between failure, okay? So now we calculate, this is where we have the how much failure per year. Okay, so the mean time between failure is equivalent to 1 over mu, which is 1 over 2.03, 0.4926. So meaning every year, this the time that you have between this failure is 0.49 per year. Okay. So in other words, if let's say we times by 12, okay, we are expecting the system to fail 0.926, oops, times 12. We are expecting it to fail every 5.9 months. Okay, got it? So in that case, if we want to schedule a PM for this equipment, okay, means we will have to schedule it every 5 months or even every 4 months once before the failure started. Okay, got it? Okay, if any questions so far for this calculations of mean time between failures, very simple calculation. It's just that this data, the most important thing is to get this data here, this one. The selected process, the instruments, the failure per year. Okay, how do we get all this beautiful data, the fault per year here? So this data is readily available. You can get it from the textbook, or you can get it from the websites. They talks about that if let's say you go to CHE6, the chemical process plant index, okay, it will tells you all these data like the failure rates and what is the cost index for the year, etc. So all these data are readily available and it has been kept up to date. Any questions so far, class? If no,
No,
then we,
Miss.
okay, good. If no, then we go to the second part of second questions. Okay, the water storage tank in this below figure, figure 2, is the standard storage tank for water and chemicals. Overfilling of storage tank is a common issue. And to prevent overfilling, the storage tank is normally equipped with high-level shutdown system. The high-level shutdown system is connected to a solenoid valve that stop the flow from input stock, which if let's say I'm going to enlarge this, what happened is that to prevent it from overflowing, okay, so if let's say this one to stop it from overflow, we have a level sensor. So we call it level transmitter or level sensor. Okay, that goes to a level controller. So when it hits the maximum here, what happened is that it will off the valve. As simple as that. Okay. So now we want to calculate that what if this fail? Oops, I need to make it small. Oops, now this is not working. Hold on, my iPad hang. Okay. Okay, so first we develop an event tree, okay, for the system using the failure of level transmitter. Oh, this is too small now. So what if this guy fail? Okay, if this guy fail, what happened? It will be definitely an overflow. Okay, so failure of level transmitter as an initiating event, given that the level indicator fail 5 times a year, so the mu here is 5 times per year. Okay, estimate the number of overflow expected per year. Okay, and use the following data. So we have the high level alarm, and then of course when the alarm rang, the operator will stop the flow. Okay, and also we have another high level switch systems is where if when the alarm rang, okay, it triggers only when the alarm rang. So if the alarms doesn't ring, because that's the switch system, if the alarm doesn't go off, then it will overflow as well. Okay, so let's start. So our event, so let's put as ABC. I like to do it that way. So A, the event is how we have this level controller system. Failure of level controller. Okay. As the start event. Okay. Then our first event is if what will happen. So if this failed, what's the next failure? The failure will be it start to hit a very high level. So you have alarm. Okay. So high level alarm. Okay. And when the high level alarm hits, there are two things. One is where our switch system, high level switch system kick in. Okay. If let's say this fail, the next one is where we have our operator to stop flow. Okay. So, and operator to stop flow is when the high level alarm rang, or unless we assume, because this one, there are few scenario is that operators will only solve it when the alarm rang, or operators are very alert even without the alarm, they notice that. So it really depends on how you want to craft your scenario. Okay, so we will craft the scenario saying that assuming that they are very alert. Okay, so meaning even without the high level alarm, they will off the WAF. Okay, very alert. So with or without the alarm system, the operator off it. You later we are going to do both, so you can see like what is the difference between having like operators being alert and operators not being alert. But that impact is very small compared to the alarm system. Okay, so come, let's do this. So high the alarm, we can pass, we can fail. Okay, so this one, the failure is 5 per year. Okay, so then we have this success. If let's say the high level alarms go off, okay, so most of the time it will tell us the 99% of the time it succeeds. So this is 99% of the time, but 1% of the time it failed. Okay, so when it comes to the next system, okay, so remember just now we mentioned this high level switch system trigger only with alarm. Okay, so when the alarm kick in, this system kick in. So it will trigger. So 99% of the time it triggered, it will switch it off. So the system is safe. You won't have the overflow. But there is 1% of the time that it failed. Okay. So when it failed, what happens? Of course, because of the alarm rang, we assume that the operators are there being able to stop flow. And if you look at this, operator stop flow, the failure per demand is zero point 0.2, meaning 20% of the time that they fail to stop. Okay, where this is where we have overflow. Okay, 80% of the time it will get to stop it. So we have a safe system here. Okay, so now the last part. When the high level alarm is off, this route, this specific route. So when there's no high level alarm means there is no system trigger, we basically bypass this. And that is why just now we said we have to decide whether is our operator alert with or without the alarm. Without the alarms, if they are alert, good. Okay, so now we are assuming that they are so good that they will notice that without the alarm, they will save, they will notice it and they will stop the flow. So again, 80% of the time that they do that, 20% of the time they fail. Okay, so this is safe. And again, this is overflow. So now we want to calculate how often that this system fail with this setup. Okay, the level control failed 5 times a year with our high level alarm in place and also high level switch system in place. Let's calculate that. Okay, so now I'm going to highlight this. So let's look at the overflow first, the X. So there's one route from here that go here. Okay, and there is a second route. Let's use a different color. From here to here. Okay, so we have two routes. So failure per year, or the what we call the overflow per year, is where we have route 1. Okay, so 5 times per year it failed. Okay, and 0.99 times the 0.01%, the 1% here, and also the 20% of operator didn't manage to stop the flow. And also the second route is where the high level alarm failed and the operator didn't manage to stop the flow. Okay, let's calculate this. So we have times 5. So we have 0.0199 overflow per year. Okay, so if let's say we times with 12 months, it's like 0.23 months. So failure per year. Okay, sorry, what is... So we get 0.0199 per year. Okay, so meaning if let's say we want to calculate the mean time between failure, So what it tells us is that if, let's say, this system, okay, this how to say, the uh, the level control fail 5 times a year, but with our system in place, we have the high level alarm in place, we have the high level switch system in place, the mean time between failure, so the whole system get overflow every 5.02 years. Okay, so in fact, this is still very high, means every 5 years we expect there will be one overflowing cases. Okay, so but if, let's say, for example, if we remove certain things in here, okay, like just if we assume a different scenario, okay, where um our operators only react with alarm, you will notice the level goes up. Okay, so meaning over here it will just be this all the way and it failed. Okay, so the the overflow per year for the second scenario will be, the first route is still the same, means when the alarm rang, the operator will react. Okay, so you get like 0.99 times 0.01 times 0.2 plus the last part is 0.01. That's it. So 0.99 times 0.01 times 0.2. Okay, plus times 5. So immediately you notice that this increased 0.0599 per year. And your mean time between failure is 1 divided by 0.0599. Oh, I think I did a mistake here. 1 divided by 0.0199. Okay, sorry. This is not 5 years, just like I forgot the zero. This is 50.25 failure. Where is my this one? So every 50.25 50 years, it will have one overflow, okay, with this system setup. But if, let's say, we assume that the operators are just not aware of what is going on, they will only react with the alarm. So you will see that this level of potential overflows has cut down to become 16.7 years. So meaning every 16 or every 17 years, you'll definitely experience one overflow incident. Why is this data important? Anyone? Any idea? Like, why are we talking about like overflow every 50 years or overflow every 16 years? Okay, just by having operators who are alert or operators who are not alert. The reasons we are looking at this is that if, let's say, this is water overflow, no big deal, you waste some water. But imagine that this storage tank is not water, but is a fully concentrated acid, and there's an overflow. Or fully concentrated, highly vaporized chemical or highly volatile chemicals. Then we might experience explosions, we might go through acid burns or contaminations, etc. So even for simple things like that, like overflowing, looking at the control system, is that sufficient? Is that too low? Is that too high? Is this mean time between failure acceptable? Especially for chemical process plants, is very important. So even for 50 years once, this value is still high. And this is only by the change of, like, we assume the operator doesn't really notice if there's an overflow coming up. If, let's say, for example, you have a fully enclosed tank where they will only see when it's overflow, that's already too late. Okay, that incidence might just cut down that potentials of incidents might just increase from 50 years once to 17 years once. And that is actually very serious. Okay, so any questions so far? So how do we improve this? If, let's say, we want to further increase this 50 years once incidents to like 100, 200 years once, we can, though, just by putting up more trigger systems, or even as simple as to split up the system. What I'm saying that to split up the system is that we have this high level switch system here, as you can see. Okay, but this one is only triggered when the alarms rang. So if we disconnect the system, okay, and tie in as an individual system, so whether the alarm rang or whether the alarm doesn't rang, it will trigger first. Okay, it trigger, and then if it's fail, only then it goes to the alarms, etc. You will see that it actually changed the situation. Okay, so it becomes an individual system. So now we have to, this is how we use event tree fault tree to see how to improve the system. So let me use a different color. So can I erase this red color? Okay, so that we know that we can work on this one. So now I want to remove this one. Okay, we still keep the alarm, but we keep this as individual. So this is 0.01. Whether you have the alarm or you don't have the alarm, the system kick in, because now it is an individual system. Okay, so meaning when the alarm rang, 99% of the time it will still take care of it. It will still off it. Okay, and then 0.1% of the time it failed. Okay, and assumes that our operators only react. Okay, which is this one, only react with alarm. So this one, no alarm, is not going to react, so it's here. Okay, so let's see, now we have a different situations. Okay, so this one, this one, this one. Okay, so now let me use a different color, a purple color. Okay, so now our overflow per year will be 5. This one still same, 0 0.01, 0 0.20 plus 0 0.01, okay, times 0 0.01 times 0 0.02. Oh, sorry, there's no 0 0.02 here. Okay, so we assume that the operators will only react to alarm. So now we have 0 0.001298. Okay. Oh, sorry, I forgot to times 5. So now we have times 5, 0.00649 per year. Okay. MTBF would be 154.08 years. Just by separating, you can see from here, okay, the differences between this and this is that we separate this system, the high level switch system, instead of tying into the alarm system. So when we tie into alarm system, it will only react when alarm rang, versus it is an individual systems that as long as it triggers, it goes to that high level, is automatically switch it off. That itself increase or improve the system by reducing the occurrence. Instead of every 17 years happens once, now it's every 154 years happen once. That make the systems way safer. Got it? So the first one and the second one, this one scenario 1, scenario 2, scenario 3, is we assume or we hire a group of people who are very alert, that they know what they are doing. Okay, but most of the time humans error are there. So operators how to say, operators awareness might not be there. Okay. And the second one is where we assume, hold on, I think I have some videos on. Let me turn everything down. Okay. So the second scenario is where we assume we assumes that the operators will do their things and they will only react when alarm rang. Okay, then you can see that itself has a difference of 50 years versus a 16 years or 17 years. Whereas the third scenario is that we just separate two systems. One is just alarm only, another one triggers for whether the alarm is ringing or the alarm doesn't ring, it will trigger. And that itself save a huge number of time. Okay. Any questions so far? Okay. If no, then that's event tree. That's how we use event tree to evaluate. Do we want to, is this systems okay or is this system not okay? If it's not okay, then perhaps we add in another control level in here, or we look at the system, how we can change it, how we can modify it to improve the mean time between failure. That's the most important thing that we look at. How do we improve that mean time between failure, that we make the system reliable? Okay, Ken? Of course, beside this is just raw calculations where assuming that PM is like we don't really do a very good PM. That's the assumption. So if you do PMs and all that, you can even improve this mean time between failure. Okay. So the part B, because part A talks about event tree, that's how we use event tree to look at a simple system like this. And if we are looking at a fault tree, okay, developed a fault tree of the top event storage tank overflow and use data in table 12.1 to estimate the failure probability of the top events and the expected number of occurrence per year. Okay, what are the most likely failure modes and should the design be improved? So what we can do is very simple, very straightforward here. So we have the top events called overflow. Okay, so they are scenario. I'm going to cut down all the gates and all that. So so overflow happens like what? Let's look at this system. Overflow happens when level controller fail. Okay. And also at the same time, the control valve fail. Or if the level transmitter fail. We have three things here. So we are going to focus on these three things. Okay. So overflow here is where level transmitter, okay, and then we have a second one is the valves, and also we have a third ones where is the level controller. Okay, so is this an AND gate or an OR gate? I believe this is an OR gate because if your level transmitter fail or your valve fail or your level controller fail, none of this will happen. The whole system will not function, meaning either one of these elements fail, you will immediately have an overflow. Okay. So again, if let's say we look at this becomes the first questions again. So we have a controller fail, 0.29. We have a control valve fail, 0.6. And we have a flow measurements fail. This is not flow measurements. This is a level indicator. Let's see. Level indicator fail is 1.7 for liquid. Okay. So you can see that the data's here. So we have controller. We have control valve, 0.29, 0.6. Okay. And then we have okay, where is my level? Level measurements, 1.7. Okay. So if any of these three fail, what is the failure per year? So go back to the first questions where the reliability of each, the reliability of each is e to the power of negative mu t, okay, for per year. So the reliability of the level transmitter, okay, over here, the level measurements is E minus 1.70. So do we have the data? Exponential minus 1.70. So we get 0.1826. Okay. Reliability of the control valve, 0.29. I think we have it earlier, 0.7483. And this is controller, not control valve. And then the valves. Point 0.5488. So when we say if it is an OR gate, so what happened is that the reliability goes down. So when it is the OR gate is where you times all, okay, where 0.1826 times 0.7483 times 0.5488. So you have the overall failure as 0.07499. Okay. So now we want to know the overall mu here is where we have negative ln. Anyone has an answer for this? Okay. 0.07499. Okay, so I got as 2.59. Thank you, Elena. 2.59. Okay, fault per year. So the mean time between failure of the system is 1 over 2.59. 0.386 years. So it's also equivalence if we times it to months is every 4.6 months. The system will have an overflow. Okay, got it? So this is to calculate the systems itself, like the potential of system overflowing. But this eventually tell us how we can prevent it, how we can reduce the overall system failure. Okay, this is just to calculate, okay, when we have these three, what is the potential or how often that it fail and that we want to take action. Got it, class? So fault tree will help us to identify like how often we want to do a maintenance for this system, for these three valves, the three elements, three instruments here. We have control, level controller, we have the valve, we have the level transmitter. How often do we want to look at all of this to prevent the failure? Okay. And event trees work slightly different. It doesn't tell us like how often we want to do PM because we wouldn't be doing PM once every 154. That's ridiculous. But this will tell us with these systems that we have in place, how often that the events of overflow occur. So the two of them are different. Got it? Can see the differences? Class?
Yes, Miss.
Okay. Any questions so far? Because I think that concluded our whole semester study. So in chapter 1, we talk about introductions. We talk a little bit about statistics, how to calculate those OSHA incidence rate. So we'll just go through a very quick revision, yeah? So talk about OSHA incident rate, talk about FAR level, okay, the fatality rates and all that, okay. So that's in chapter 1, the first lessons that we have talking about safety statistics, okay. And then chapter 2, we talks about toxicology, how toxicants enter our body and how does it being eliminated from our body. To know that so that we will know how to prevent it. Or if, let's say, in the events it went into our body, what can we do? And we also talks about the calculations of the threshold limit in chapter 2 and then go branch into chapter 3, talking about the total exposure. How long can the person's being exposed if let's say the level is at the lower than the threshold limits, then you can expose it up to 8 hours, doesn't matter. But the moment it hits certain limits, that what is the regulation? Like if when it hits the STEL level, there's only 15 minutes exposures with a 1 hour break and go back for a 15 minutes exposure, etc. So that basically talks about lots of calculations in that chapter 2 and 3, talking about the probit equations, like talking about death rate. If let's say a person, people being exposed, there's a gas leaking, for example, for the durations for 2 hours, and that's the concentrations. What is that severity? That tell us how much chemical we can store in a process plant. Because if let's say the level is too bad, then we may want to see how we can reduce the storage of those chemicals. Yeah. So that's chapter 1, 2, and 3, talking about the toxicology and industrial hygienes. Chapter then we went into the safety, the hazard analysis and hazard identifications. We talk about how to identify hazards, how to do hazard analysis. Hazard analysis is a tool for us to see how we analyze, like, what do we want to do? What is the action plan? If we have this, what else can go wrong? Okay, in the qualitative way of measurements, means there's no number in all those hazard analysis. Like hazard has no numbers involved. It's just like too high, too low, what happened? Too hot, too cold, what happened? Overflow, reverse flow, what happened? Okay, what might go wrong? It's all on quality assessment, qualitative assessment. And this chapter is more quantitative assessment. We put everything into a numbers to see, is this okay or is this not okay? So that's the biggest differences between a hazard analysis versus inventory and forestry. Inventory and forestry often give us numbers. Okay. Hazard analysis or hazard doesn't give us a number. Got it? So that's the biggest difference. But these are all tools that use in industry. So it's not to say one is better than the other, but their usage are different. Okay, so for your final assessment preparations, definitely there will be questions that require you to use tools. So tool selections itself is important. You have to see, do I want to use hazard for this scenario? Because not every cases you use hazard. Sometimes is where you want to use inventory. There are times you want to use forestry. Okay, forestry again is for us to identify how frequent the things break down, and if I want to plan for preventive maintenance. Like I noticed that from your assignments, when you do hazard analysis, you like to put in like preventive maintenance, very frequent, like in work case, like when you start to work, we can't put that as a suggestions, because people will look at it and say, how frequent is frequent? Every week, every month, and all that. So from there, then you want to do this for three calculations, or to do just simple failure calculations to calculate, to estimate the mean time between failure. Then you tell them, you give them suggestions. Oh, the maintenance should be done every 5 months, every 4 months, to prevent it to break down. So marks will be given, especially in your final assessment, when you do hazard analysis and you back it up with a probability calculation like this, to say, because I know students like to give me, oh, do PM, frequent PM, more frequent PM. And when we say frequent PM, we need to tell the system how much. How frequent is frequent? How long? That what's the durations that we should be conducting a PM? Okay. So that's where the marks given. If you just say do PM, there's no marks given for the suggestions. And also, if you're doing hazard analysis in your final assessment, I will focus more on the suggestions that will prevent it from happening, or what we call inherent safety, not just preventive, but to build in a safety system that's inherent, like reducing the chemical flow, reducing the temperature, for example, of the reactor, etc. Okay, so those are the things that I will be looking at. Of about 50% of your final assessments look at hazard analysis, meaning that hazard evaluations, not hazard itself, but hazards evaluations, meaning looking at also looking at SDS. What are the chemicals? Remember, we did an assignment, a tutorials talking about how to look at SDS and to see, oh, this has a TWA ceiling of 5 ppm, and this is very hazardous. This is very volatile. It killed people's or with just a tinge of spillage, etc. Okay, so 50% of this whole final assessment talks about how you review safety. Okay, and then 20% asks about your understanding about safety. So those answer you can easily find out if, let's say, you follow the lecturers, or even you can Google some of the answer. But even if you Google them, please write it in your own words. Yeah, don't just copy and paste, because turn it in works. Okay, you write it in your own understanding. What are those things? That's 20%. And the other remaining 30%, look at, after you review safety, what is your action plan? Okay, that involve very minimal calculations. If there is really really minimum, but it focus more on the decisions making. It focus more on how you review safety. And also a very short tips for all of you is that some of these questions are related to your assignment one. Okay, so that's a heads up. Any questions so far? Oh, okay. And also we look into fire and explosion. That's the very big chapters when it comes to safety in chemical plant. Yeah, because a lots of mishaps results in explosion. Okay, and also it's not just explosions, but it can be vapor gas explosion, means there's no fire involved, but it's just release or spillage of chemicals. Yeah, like for example, a very good example is the Bhopal, India Bhopal incidents. There was no fire, but there was this pesticide released into the whole city, and overnight it kills about 200,000 people in that city itself, just overnight. And then until today, after like 20 over years, the long-term effect is still that people are still born. They are babies born without a hand, without half a lung, and all that, due to those toxic, due to the effect of this propa gas release, the pesticides gas release. Okay, those are the long-term effects of the populations of people in that area. So we will, some of these questions will always relate to cases like this. Okay, so fire and explosion is a big chapter. Even for those who are about to go to work, because I believe some of you are taking this as an elective in SEM 7 or SEM 8. So the moment you go out to work, always put safety in mind. Always safety come first. Everything else talk later. Not money come first, but safety come first. Okay, safety includes physical safety and also health safety. Any questions so far? I believe I covered all of it. And then the last chapter of this one is all the codes. Those are for your knowledge. You just have to read like what are the codes and conducts. Any questions so far? This module is not tough. Okay, it's easy to pass. But it's very tough to get A though, to be honest, because we look at the decisions making and we focus a lot of inherent safety. Okay. Any questions, class? If no, I think that's about it. Our tutorial and also a quick revisions of what to expect. And also don't forget to do your assignment 2 that is due on Friday, I believe. And I received a few students request to extend it. The answer is no, because I have given it to you all for a very long time for this assignment. So it's just to attend those safety courses and get the certificates and just write about 50 words about that course. That's it. Don't give me a thesis on that because the moment you have the certificates, that certificates is a value added certificates for your CV. Okay, because that is an international certificates for chemical engineers. Okay, so if you want to apply for job in the future in Petronas, in Shell, in all the oil and gas or even oil and fat, they will look at the certificates. Yeah, because that shows values. So keep those certificates, don't lose them. It's e-copy, so just save it in your computer and also in your profile. As long as you keep your accounts active in the iChemie account active, you can always retrieve your certificates in there. All the SACHE certificates are free for undergrad. So get it while you are still an undergrad. Okay. The moment you graduate, they will change your membership to normal membership. That's where you will start to pay for all those courses. Each course is about 199 USD. So get it while it is free. It's really good for you to build your profile, to build your CV. Okay, if no, all the best. And for those who are struggling with your or who are preparing for your Eureka presentations in the afternoon, all the best. And those who already over, then just let it go. And those who are preparing for your thesis defense tomorrow or next week, all the best as well. Okay, I'll see you all next semester then. Take care. Bye bye.